Wait, how do images enlarge? This question came up to me one day when I thought about how images are made of pixels, and when an image is enlarged, a gap is created between those pixels. So how does the computer fill them in? Now, there isn't really one solution to this problem. You can technically fill these gaps with whatever you want and still get some kind of validative and interesting results. But when we're looking for something that actually looks like a cleanly enlarged version of the original image, we need to find something a little more specific. We can start by breaking this problem down to its most basic form, an image made of 2 pixels. Here, all we need is to think how we fill this one line of gap. Once we do that, we can apply to any 2 adjacent pixels in the original image. Of course, the way we fill in this gap should be any random thing which comes to mind. We need to fill these pixels in a way where their colors start closer to the first pixel and slowly become more and more similar to the second one. We may also demand that these colors stay in the range between the 2 original colors, and maybe also that the rate in which the color changes doesn't speed up or slow down. Let's try to visualize this for a moment. As I'm sure many of you are aware, digitally, colors are stored as 3 numbers corresponding to red, green, and blue. Well, this kinda looks like a coordinate system, doesn't it? RGB, XYZ, what's the difference really? Just letters. So just as easily we can visualize colors as points in 3-dimensional space, where XYZ correspond to RGB respectively. Note, this version of 3D space is limited to XYZ values which are positive and limited by some upper bound, which in our case is 255. Now back to our problem. We have 2 colors and we want to insert colors between them, according to our previous demands. Well, the most obvious path between 2 points is of course a straight line. So to sum up, we are looking for a way to insert colors along a straight line. Of course, linear interpolation is the answer. To any of you unaware, linear interpolation, or lerping, is a way of inserting points along a straight line, which is exactly what we need. Now, I'm a big believer in knowing where anything and everything comes from, so I'm just gonna add this little part here which starts from our basic demands and arrives at the formula for linear interpolation naturally, which I think is amazing. Let's formalize some things first. Define a color as a point or vector in 3D space. Now suppose we have 2 colors, C1 and C2, and a function defined for these 2 colors, f of t, where t ranges from 0 to 1. You could think of t as a measure of how far you've gone between the 2 points, where 0 is the start of the path at C1 and 1 is at the end of the path at C2. This already takes care of our first demand. The next 2 are a little trickier. We first need to think of the derivative of f at some point. This represents the speed of which the point moves along the path, and its direction. Now we could take our third demand and rephrase it like this, meaning the speed of which the point moves along the path is some constant which will denote v. As for our second demand, we can rephrase it as the colors do not change direction when moving, and so the speed and direction of the colors stay constant throughout their motion, which is represented by this constant vector. We can now integrate this expression and get the following formula, where r0 is another constant that came up from integration. We can now plug in f of 0 and f of 1 to get the true values of r0 and v. After all the dust settles, this is our final formula. Let's take a second to admire what simple beauty this function is and how much sense it makes. It begins at the start of the path and slowly adds a fraction of the path until it reaches the end at 100%. Now back to our formula. Let's factor this a little bit. This is a different way of looking at exactly the same formula. This time we can see the contribution of each color by itself, which in total add up to 1, as some kind of weighted average between the 2. So there we have it. If we have 2 points, we can interpolate between them using this function. Addition and multiplication work with colors just as with any other vector, where you add or multiply each component on its own. Of course, this whole problem arose because the pixels are not a continuous line, but discrete objects, and so are the new pixels created. So when the image is enlarged, we need to re-index all these pixels by their new order. We'll call this a scaling factor of 3, as the distance between the original pixels has been scaled up by 3. Now that we have our enlarged image, or some skeleton of it, let's take some pixel and lerp on it. All we need is RT, which can be easily calculated as the distance between that pixel to the start of the gap divided by the total distance, which is just our scaling factor. Notice how this yields 0 on the first pixel and 1 on the last, just like we want. It's important to remember that we need to calculate this distance using a certain point on the pixel, like the end or the start or the middle. Any of them yield the same result, as long as we stay consistent. Now let's plug it into our formula and see what we get. Notice our new notation here, where C denotes colors from the old image and C prime denotes colors in the new image, and the subscript defines the index in which the pixel is located. We can see that here we interpolate between the original pixels at position 0 and 1. Now we can finally perform our calculation, from which we get this purple color. Now we can also perform our calculation for the second pixel, and voila, we have a completed image. Now this is for only 2 pixels, so let's look at the bigger picture. Suppose we have a string of say 5 pixels, which we enlarge by a factor of 3, and we want to interpolate between the pixels at indices 2 and 3, which in the enlarged image sit at 6 and 9 respectively. So for some pixel between them, let's say at index 7, our t will be the distance from the start of the gap, which is 7 minus 6, or 1, divided by the length of the gap, which is 3. So the color at index 7 will look like this. We can repeat this process for all other gap pixels until the image is fully constructed. Let's run it back to the start of the process. We have the original image and the enlarged version with all its gaps. We want to find out what color this pixel will be. Easy, just slur between the start and end pixels just as before. But what are the start and end pixels? You can say that it's super simple, just find the first original pixels before and after this one and use those. But remember that overall this process needs to be done by a computer, and using some kind of while loop to go back until you find a multiple of 3 is a really wasteful task, which only gets harder and even useless when you scale by a bigger or non-whole factor. What we can do is use the base pixels property, which says that the base pixels sit at whole number indices in the original image. Because we get the new indices by multiplying by 3, we can easily get the original index from the new one by simply dividing by 3 back. But this time we can do this not only to the base pixels, but to the gap pixels as well. Here we see the much clearer distinction. When dividing by the scaling factor, base pixels get a whole result, while gap pixels get a fractional result. And the difference between whole and non-whole numbers is much clearer than the difference between numbers that are a multiple of 3 and ones that aren't. We can think of it like this. In the original image, between any 2 adjacent pixels, there is a hidden range of colors which sit at the real valued positions between their whole indices, but the computer can only display colors at whole valued indices, so these are the only colors which are seen in the image. When the image is scaled, the range between these pixels is stretched and now sits upon some whole number indices, which can now be displayed by the computer. So now that we know that the gap pixels correspond to some virtual fractional position in the original image, we can get the closest whole index before them by using the floor function, which gives the closest whole number before some given real number. And so, for an image scaled up by some factor alpha and an index p, its position in the original image is p over alpha, and the colors we need to interpolate between are the floor of p over alpha and the floor of p over alpha plus 1. And our t, which we'll again calculate by the distance between the pixels divided by the scaling factor, looks like this. Finally, we can plug everything in and get our final formula. This is getting kinda ugly, so let's introduce some definitions. We'll define w alpha of p as the index in the original image of the closest base pixel, or the whole part of this index, and f alpha of p is the fractional part of the index. By these definitions, w of p dictates which 2 pixels the new color is between, and f of p says where the color sits in the range between them. So now we have our new form of the formula. The color in the new image at index p is given by a linear interpolation between the colors of the original image at indices w of p and w of p plus 1 with t equals f of p. I think by now we all understand that these colors are vectors, so we can get rid of the arrow to make it a bit cleaner. Any of you familiar with some linear algebra may call this type of formula a linear combination. And in true linear algebra fashion, we can express an image as a column vector of colors. Note how there are two types of vectors here. The vectors which represent the color itself, and the column vector which holds all the colors in order to form an image. Now we can plug in some values. And here some of you might see how this can be expressed in the form of matrix multiplication. Notice how all these zeros come up, because for each pixel the interpolation happens only between two base pixels, and the other ones don't matter, which is identical to giving them a weight of 0 in our calculation. Especially in the case where a certain color is just copied from the original image, that color is giving a weight of 1 and all others are given a weight of 0. What's great about this form of the equation is that the matrix is independent of any values from within the colors themselves, and so it could be applied to any one-dimensional image of length 7. And of course, we can very easily change it to any lengths of image and any scaling factor by just slightly altering the matrix. We can look at the matrix this way. The vertical index I represents the index in the new image, and the horizontal index j represents the index in the original image. Because of how matrix multiplication works, each row contains the coefficients to use when constructing the linear combination for a specific pixel at index I. Take for example the new pixel at I equals 1, and see it is 2/3 of the original pixel at index 0 and 1/3 of the original pixel at index 1, and so on for all other new pixels. Specifically for the original pixels, you can see they are constructed simply by 100% of themselves, as no combination is necessary. Well, effectively, this matrix acts as some sort of transformation on these images, and therefore will denote T. This transformation can be applied to any image Cj by multiplying it from the right. Effectively how this works is the index which is repeated in both parts, in this case j, is summed over. When substituting the formula we know from before, we can understand what values t needs to have as dependent on I and j. Here, for example, we know j equals w of I, and therefore the value of t at this I and j equals w of I is this. The same also applies for w of I plus 1, and for all other values of j, it is 0, as the interpolation happens only between these two pixels. Let's now introduce some new notation, the Kronecker delta. This lowercase delta is some kind of function that takes in two variables and is defined like so. If the variables are equal to each other, the function takes a value of 1, otherwise it takes a value of 0. This means we can rewrite our huge formula as something like this. And so, whenever j equals w of I, this delta is 1 and the other is 0, that we are only left with the expression needed for this particular index, and similarly for w of I plus 1. When j is different from both of these values, they are both 0, and the whole expression is obliterated from existence just like we wanted. This way, when summing over the index j, whenever it is different from w of I and w of I plus 1, the pixel corresponding to it becomes 0, meaning it isn't used, and when it is equal to one of them, our t becomes the correct coefficient for that pixel. And so in total, we are left with our original formula. To make things even nicer, we could do something like this. I just moved all the indices with an I in them a little higher. Now it's very important to remember that these things are not exponentials. They are superscript indices, which are like Norman indices, but they appear at the top. We'll also change the index in the image vector to also be in the superscript. This notation is commonly used in tensors, and these things are like tensors in their most basic form as multidimensional arrays, which have an assigned value for each set of given indices. When we just have two indices, this is practically the same thing as a matrix, but it will come in handy when you have more than two. Tensors have much more fascinating and useful properties in mathematics and physics, which I will not discuss here. What we do here is sum over the indices which cancel out, like we've seen before, and the indices that don't are carried over to the result. For one-dimensional images, it just acts like matrix multiplication. One disclaimer is needed here. Because this matrix is mostly zeros, actually generating the new image by our method is really wasteful and borderline stupid, because most of the runtime of the computer will be used to multiply zeros by a bunch of stuff, which does take non-zero time, and the bigger our matrix is, the more runtime will be wasted on multiplying these zeros instead of just skipping these steps entirely and just using what is really needed for interpolation. However, this video is not meant for maximal computational efficiency, it's for education and fun. Speaking of fun, Nothing in this formula forbids us from plugging in a fractional scaling factor, or even an irrational one. So you could scale an image by a scaling factor of pi, although the final values will be rounded. You might notice that in this case the original pixels disappear in the new image, as they now sit in non-whole indices which we do not display. Even factors which are smaller than 1 work. We can use this to scale down a larger image, or one we've enlarged ourselves, and see we get the original one. So now we know how to scale an image to any size we want. Phew, what a journey. That's all for now, and I'll see you next time.
Wait a minute, you mouth out at your screen, angry and frustrated. I came here to learn how to enlarge an actual image, not some random line of pixels.
Oh, right. 2 dimensions. Well, that isn't too complicated. Now instead of 2 adjacent pixels, we have 4 in a square. Let's scale them up by some factor. Whoa, those are a lot of new gap pixels. We can use our cool transformation formula to interpolate between the edges, but what about the gaps in between? Well, that's simple. Just interpolate again. This does make a lot of sense. Because we've jumped up 1 dimension, we need to interpolate an additional time in order to take into account all 4 corner pixels instead of the regular 2. We can even see that it doesn't matter which axis we interpolate on, the result stays the same. This method is called bilinear interpolation. Yes, I know, quite a shocker. If we factor this expression like before into the form of a linear combination, where each pixels of the original image is multiplied by some coefficient, you can see the logic that arises behind this new two-dimensional interpolation. Instead of a weighted average according to the closeness to each pixel, we use the area to each pixel as our new weights. Take C00 for example. We can see how its coefficient is 1 minus f of I times 1 minus f of j, which is just area d divided by the total area alpha squared. Generally, each corner pixel uses the area opposite of it divided by the total area as its weight. We can now generalize it like before, so instead of just using the pixels at 0 and 1, we can find the general index by using our w function for I and for j respectively. Back to our formula. We just plugged back in the values for these areas. Really, what makes these coefficients areas is that they have 2 factors, one dependent on I and one dependent on j. We can see that for pixels with the same first index, the factors that are dependent on I are also the same, and that also applies for the second index and the factors that are dependent on j. Generally, we can describe each coefficient as a product of 2 factors, one as a function of the first index, which we'll call k, and the other as a function of the second index, which we'll call L. And in total, this whole thing is multiplied by the pixel at indices k and L. This was done here by the same method we used for one-dimensional images, where we looked what our index equals and by that defined what the coefficient will be at that value of the index. This whole thing is our transformation. But now it has 4 indices, 2 at the bottom that take care of the original image and 2 at the top, which represent the new scaled image. Because there are now 2 indices which cancel out, we need to summon both of them. We'll see how that works in a moment. If you look closely at these factors, you might notice that they are actually both the same thing, just with the change of index names. And not only are they the same, they're both equal to the one-dimensional transformation we had before. So the new two-dimensional transformation can be expressed as the product of 2 one-dimensional transformation factors. That's cool. And now comes the visualization part. Well, because this tensor has 4 indices, that means it's 4-dimensional. And because our universe is infamously known for only consisting of 3 dimensions, it will be a little difficult to visualize. We can, however, visualize it for a construction of a single pixel, as setting these 2 indices to some constant values, we are only left with 2 free indices, meaning a 2-dimensional tensor, which is very easily visualized as a matrix. So let's take some image and scale it up. We'll pick some pixel here and see what happens when it's constructed. We know that our pixel is C' at 510. We also then know that it equals our 2D transformation tensor with constant superscript indices 5 and 10 and subscript indices k and l, multiplied by our original image ckl. We already know what our image looks like, and our transformation matrix for this pixel turns out to be this. This time, Because we have two indices which cancel out, we need to summon both of them, which in total sums the products of each of these values with their corresponding pixel. Notice how all pixels get a coefficient of 0 except the 4 which surround our new pixel. The resulting color is this kind of dark lavender, which we can insert into our new image. We can now repeat this process for each and every pixel until the full image is finished. What a beauty! Of course, this process is a little tedious, but doing it by hand is unnecessary when things like NumPy's tensor dot function exist. Wait, I just had a crazy thought. If the 2D transformation is just a product of two one-dimensional transformations, then what's stopping us from adding another one? This way, we can transform three-dimensional images, and if we add another one, we can transform fourth-dimensional images. But I don't think I'll even bother with this one.